Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. The quest to visualize the intricate machinery of life at the smallest scales presented a formidable challenge in mid-20th century science. Optical microscopy, while invaluable, faced a fundamental limitation: the diffraction limit of light. This physical constraint restricted resolution, preventing the detailed observation of structures smaller than the wavelength of visible light. Electron microscopy offered a path to higher resolution, employing electrons with far shorter wavelengths. However, this technique demanded a high vacuum environment, a condition utterly incompatible with the delicate chemistry of living biological systems. The vacuum's destructive nature rendered electron microscopy ineffective for imaging living cells in their natural state. A significant scientific hurdle remained: developing a method to image living biological systems at a scale surpassing the limitations of light microscopy, while avoiding the destructive effects of electron beams. This challenge spurred a search for alternative approaches, focusing on radiation with wavelengths sufficiently short to overcome the diffraction barrier, yet gentle enough to preserve the integrity of living specimens. X-rays, with their remarkably short wavelengths, emerged as a promising candidate. Their penetrating power suggested the potential for non-destructive imaging. However, manipulating X-rays for microscopy proved exceptionally difficult. Unlike visible light, X-rays interact weakly with matter, making it extremely challenging to refract or reflect them using conventional lenses or mirrors designed for visible light. The creation of an X-ray microscope, capable of resolving fine biological structures, seemed, to many, an insurmountable problem. Albert Baez, a physicist with a keen interest in the intersection of fundamental physics and practical applications, recognized the significance of this challenge. He understood the profound implications of developing a high-resolution, non-destructive imaging technique for biological research. Working alongside Paul Kirkpatrick, a fellow physicist at Stanford University, he embarked on a pioneering endeavor. Their collaboration led to a groundbreaking solution: the invention of the X-ray reflection microscope, a system now known as the Kirkpatrick-Baez KB system. The ingenuity of the KB system lay in its elegant simplicity. It eschewed the conventional approach of using lenses to focus X-rays, an approach rendered impractical by the weak interaction between X-rays and refractive materials. Instead, Baez and Kirkpatrick employed a pair of curved mirrors, meticulously shaped to reflect X-rays at grazing incidents. These mirrors, positioned orthogonally to each other, one focusing the X-rays in the horizontal plane, the other in the vertical, achieved a remarkable feat. They effectively focused X-rays to a point, creating a high-resolution image of the sample. The precise curvature of each mirror, calculated to optimize reflection efficiency at the grazing angle, was crucial to the success of the design. This elegant design circumvented the limitations of traditional X-ray optics, paving the way for a new era in X-ray microscopy. The development of the KB system was a triumph of theoretical physics and meticulous engineering. The mathematical underpinnings of the design involved a detailed understanding of X-ray reflection at grazing incidents, demanding precise calculations of mirror curvature and alignment to achieve optimal focusing. The mirrors themselves presented a considerable manufacturing challenge, requiring highly precise shaping and surface finishing to minimize scattering and maximize reflectivity. The successful implementation of the KB system demonstrated a deep understanding of both the theoretical principles of X-ray optics and the practical aspects of instrumentation. The impact of the Kirkpatrick-Baez microscope extends far beyond its initial application in biological imaging. The fundamental principle of using grazing incidence curved mirrors to focus X-rays has proven remarkably versatile and adaptable. The KB mirror configuration remains a cornerstone of modern X-ray optics, finding widespread application in diverse scientific fields. Its influence is readily apparent in numerous advanced imaging systems. Synchrotron beamlines, powerful sources of X-rays utilized for materials science research, routinely incorporate KB mirrors to focus intense X-ray beams onto samples with exceptional precision. This allows researchers to probe the atomic structure and chemical composition of materials with unparalleled detail. Similarly, X-ray free electron lasers, capable of generating ultra-bright, ultra-short X-ray pulses, rely on KB mirrors for focusing the intense laser beams onto extremely small samples, enabling the study of ultra-fast chemical reactions and dynamic processes at the atomic level. The reach of the KB system extends even to the vast expanse of space. Space-based X-ray telescopes, such as the Chandra X-ray Observatory, utilize KB mirrors to focus faint X-rays from distant celestial objects. These telescopes provide invaluable insights into the high-energy processes occurring in the universe, from the explosive deaths of stars to the formation of galaxies. The KB system's contribution to astrophysical imaging is undeniable, enabling observations that would be otherwise impossible. The enduring legacy of this invention is a testament to the power of fundamental scientific breakthroughs to shape the landscape of modern research. The elegance and effectiveness of the KB system continue to inspire new developments in X-ray optics, ensuring its place as a pivotal achievement in the history of scientific instrumentation. The seemingly insurmountable challenge of imaging living systems at the nanoscale was met with a solution both elegant and profound, a testament to human ingenuity and the power of collaborative scientific endeavor. The seemingly insurmountable challenge of imaging living systems at the nanoscale was met with a solution both elegant and profound, a testament to human ingenuity and the power of collaborative scientific endeavor. Albert Baez, having contributed significantly to the advancement of X-ray microscopy, stood at a professional crossroads. The path ahead could have led to further refinements of his optical systems, explorations of new materials, or even a deeper dive into the biophysical applications of his inventions. However, Baez felt a different calling, a conviction that his talents could be better utilized in addressing a more fundamental societal need, the improvement of science education on a global scale. The mid-20th century presented unique challenges and opportunities in the realm of science education. The post-war era witnessed a surge in scientific and technological progress, accompanied by a growing awareness of the importance of scientific literacy for both national security and economic competitiveness. Yet, many nations, particularly those in the developing world, struggled to provide adequate science education to their populations. Simultaneously, within the United States, a sense of urgency arose following the Soviet Union's launch of Sputnik in 1957. This event served as a stark reminder that American science education lagged behind its Cold War rival, prompting a national re-evaluation of curricula and teaching methods. The existing science education system was often characterized by rote memorization, a lack of hands-on experience, and a disconnect between abstract concepts and real-world applications. Students were disengaged, and the pipeline of future scientists and engineers appeared to be dwindling. Baez, a man of deep ethical convictions and a commitment to social justice, recognized this crisis and felt compelled to act. His pacifist beliefs, forged in the crucible of World War II, further fueled his desire to contribute to a more peaceful and equitable world through education. He saw science education as a powerful tool for promoting critical thinking, problem-solving skills, and a deeper understanding of the natural world, all essential for informed citizenship and global cooperation. The decision to shift his focus from research to education was not a simple career change. It was a deliberate choice driven by a profound sense of purpose. His initial foray into the world of international science education came in the early 1950s, when he accepted a position as the first director of the science education program for the United Nations Educational, Scientific and Cultural Organization, more commonly known as UNESCO. This role took him to Baghdad, Iraq, where he was tasked with establishing a physics department from the ground up. This was a daunting task, requiring him to navigate cultural differences, overcome logistical hurdles, and develop a curriculum that was both rigorous and relevant to the needs of the local community. He immersed himself in the local culture, learning Arabic and working closely with Iraqi educators to create a program that would inspire and empower students. The challenges were immense. Resources were scarce, infrastructure was limited, and the political landscape was volatile. Yet, Baez persevered, drawing on his ingenuity and his unwavering belief in the transformative power of education. He designed simple, inexpensive laboratory equipment that could be built from local materials, enabling students to conduct hands-on experiments, even with limited resources. He also emphasized the importance of connecting physics concepts to real-world applications, showing students how science could be used to address local challenges such as water scarcity and energy production. His time in Baghdad was a formative experience, solidifying his commitment to science education and providing him with invaluable insights into the challenges and opportunities of teaching science in diverse cultural contexts. He learned the importance of adaptability, resourcefulness, and cultural sensitivity, lessons that would serve him well in his subsequent endeavors. Upon returning to the United States, Baez became involved with the Physical Science Study Committee, or PSSC, a groundbreaking initiative aimed at fundamentally reforming high school physics education. The PSSC was a large-scale, government-funded project that brought together leading physicists, educators, and filmmakers to develop a new physics curriculum that emphasized conceptual understanding, inquiry-based learning, and hands-on experimentation. The project was born out of the post-Sputnik recognition that American science education needed a major overhaul. Existing textbooks were often outdated and uninspiring, and teaching methods relied heavily on rote memorization rather than fostering genuine understanding. The PSSC sought to address these shortcomings by creating a curriculum that would engage students, stimulate their curiosity, and equip them with the critical thinking skills necessary to succeed in a rapidly changing world. Baez's role within the PSSC was multifaceted. He served as a key member of the curriculum development team, contributing his expertise in physics and his passion for education to the design of new instructional materials. He also played a crucial role in the development of laboratory experiments and demonstrations that would allow students to explore physics concepts in a hands-on, interactive way. The PSSC approach to pedagogy was revolutionary for its time. It moved away from the traditional lecture-based format and embraced a more student-centered approach that encouraged active learning and critical thinking. Students were encouraged to ask questions, design experiments, and draw their own conclusions rather than simply memorizing facts and formulas. This approach fostered a deeper understanding of physics concepts and helped students develop the skills they needed to solve problems and think creatively. Perhaps Baez's most significant contribution to the PSSC was his leadership in the production of a series of physics films. Recognizing the power of visual media to engage students and illustrate complex concepts, Baez spearheaded the creation of over 100 short films that covered a wide range of physics topics. These films were not simply recordings of lectures, they were carefully crafted cinematic experiences that used innovative techniques such as slow motion, animation, and time-lapse photography to bring physics concepts to life. They were designed to be visually stimulating, intellectually engaging, and accessible to students of all backgrounds. Baez's approach to filmmaking was informed by his scientific training and his artistic sensibilities. He understood that a good science film should be both accurate and engaging, and he strived to create films that would capture the beauty and wonder of the natural world. He saw film as a powerful tool for democratizing science education, making complex concepts accessible to a wider audience. The films covered topics ranging from kinematics and dynamics to electricity and magnetism, and they were used in classrooms across the United States and around the world. They became a hallmark of the PSSC curriculum and helped to transform the way physics was taught in high schools. Baez's unique contribution to the PSSC stemmed from his ability to approach the problem of pedagogy not as a traditional teacher, but as a research physicist tackling a complex system. He applied the same rigorous thinking and experimental methods that he had used in his scientific research to the design of educational materials. He viewed the classroom as a laboratory, and he constantly sought to refine his teaching methods based on student feedback and empirical data. This approach was innovative and effective, and it helped to ensure that the PSSC curriculum was both scientifically sound and pedagogically effective. His methodical approach, combined with his creative vision, made him an invaluable asset to the PSSC team. The ripple effects of the PSSC project extended far beyond the classroom. The curriculum developed by the PSSC influenced science education standards and practices around the world. The films produced by Baez and his team became a model for science education filmmaking, and the inquiry-based learning methods championed by the PSSC continue to be used in classrooms today. Baez's decision to dedicate his career to science education was a testament to his deep commitment to social justice and his unwavering belief in the power of education to transform lives. He saw science education as a means of empowering individuals, promoting critical thinking, and fostering a more peaceful and equitable world. His work with UNESCO and the PSSC had a profound impact on science education, leaving a lasting legacy that continues to inspire educators and students alike. The transition from a promising research career to one focused on education was a deliberate and meaningful choice. Baez's decision to dedicate his career to science education was a testament to his deep commitment to social justice and his unwavering belief in the power of education to transform lives. He saw science education as a means of empowering individuals, promoting critical thinking, and fostering a more peaceful and equitable world. His work with UNESCO and the PSSC had a profound impact on science education, leaving a lasting legacy that continues to inspire educators and students alike. The transition from a promising research career to one focused on education was a deliberate and meaningful choice. Constant Total. These films were a revolutionary departure from static textbook illustrations, bringing physics to life in a way that resonated deeply with students. Another cornerstone of Baez's pedagogical approach was his advocacy for the ripple tank. He championed its use as a primary laboratory tool, recognizing its unparalleled ability to allow students to directly observe and experiment with wave phenomena. The ripple tank, a shallow tray of water, becomes a miniature universe for exploring wave behavior. By generating disturbances in the water, students could directly witness the principles of diffraction, the bending of waves around obstacles, reflection, the bouncing of waves off surfaces, refraction, the change in wave direction as they pass from one medium to another, and interference, the superposition of waves leading to constructive and destructive patterns. The ripple tank provided a tangible, visual, and interactive platform for understanding wave mechanics, transforming abstract concepts into concrete experiences. Students could manipulate the parameters of the system, changing the frequency and amplitude of the waves, the size and shape of the obstacles, and the depth of the water, and directly observe the resulting changes in wave behavior. This hands-on approach fostered a deeper intuitive understanding of wave phenomena than could ever be achieved through lectures or textbook exercises alone. Beyond his work with the PSSC films and the ripple tank, Baez demonstrated a remarkable talent for designing simple, inexpensive laboratory equipment that could be constructed from readily available materials. This stemmed from his experiences with UNESCO, where he witnessed firsthand the resource constraints faced by educators in developing countries. He understood that access to quality science education should depend on ingenuity and resourcefulness, not solely on expensive equipment. He embraced the challenge of creating effective teaching tools from everyday items, thereby democratizing hands-on science education on a global scale. For instance, he devised experiments using simple lenses and mirrors to demonstrate the principles of optics, employed readily available electronic components to build circuits, illustrating basic electrical concepts, and utilized household materials to construct models of mechanical systems. These low-cost apparatuses empowered teachers in resource-limited settings to provide their students with engaging and effective science education, fostering a spirit of innovation and problem-solving. The impact of Baez's pedagogical innovations extends far beyond the specific tools and techniques he developed. His underlying philosophy of inquiry-based learning, coupled with his emphasis on powerful visual demonstrations, has become a central tenet of modern STEM pedagogy. He recognized that true learning occurs when students are actively engaged in the process of discovery, when they are encouraged to ask questions, formulate hypotheses, and test their ideas through experimentation. His work with the PSSC films and the ripple tank exemplified this approach, providing students with opportunities to explore, experiment, and construct their own understanding of the physical world. His commitment to low-cost apparatus further reinforced this philosophy, empowering teachers to create engaging learning experiences regardless of their budgetary constraints. The ripple effects of Baez's work continue to resonate in classrooms and educational institutions around the world. His emphasis on visual learning has influenced the design of countless science education resources, from interactive simulations to educational videos. His commitment to inquiry-based learning has inspired educators to adopt student-centered teaching methods that promote critical thinking and problem-solving skills. His legacy is one of empowerment, providing both teachers and students with the tools and the mindset needed to explore the wonders of the physical world. His approach was a conscious rejection of passive learning, advocating for active participation, experimentation, and a deep engagement with the underlying principles of physics. He fostered an environment where students were encouraged to challenge assumptions, question authority, and develop their own independent thinking. Baez's dedication to education extended beyond the creation of films and teaching aids. It found perhaps its most comprehensive expression in his textbook, The New College Physics, A Spiral Approach. This was no conventional physics textbook, adhering to a linear progression from mechanics to thermodynamics to electromagnetism. Instead, Baez envisioned a curriculum where core concepts were revisited repeatedly, each time at a higher level of sophistication and complexity. The spiral approach recognized that true understanding is rarely achieved in a single pass. Students initially encounter a concept in its simplest form, grasping the basic principles. They then circle back to the same concept later in the course, but this time with a more nuanced perspective, incorporating additional mathematical tools and real-world applications. This iterative process allows students to build a deeper, more robust understanding over time, reinforcing their knowledge and solidifying their grasp of the fundamental laws of physics. Imagine, for example, the concept of energy. A traditional textbook might present energy in a single chapter, covering kinetic energy, potential energy, and the conservation of energy in a linear fashion. Baez's spiral approach, however, would introduce energy early on with simple examples, such as the energy of a falling object. Later, the concept would reappear in the context of thermodynamics, where students would learn about internal energy, heat, and entropy. Finally, energy would be revisited again in the study of electromagnetism, where students would explore the energy stored in electric and magnetic fields. This cyclical approach allows students to progressively deepen their understanding of energy, seeing it from multiple perspectives and appreciating its central role in all areas of physics. The textbook's structure reflected Baez's broader philosophy of education. It was designed to encourage active learning, critical thinking, and problem-solving. Each chapter included thought-provoking questions, challenging exercises, and real-world examples that prompted students to apply their knowledge in meaningful ways. The book also incorporated a historical perspective, highlighting the contributions of scientists from diverse backgrounds and showcasing the evolution of scientific ideas over time. The New College Physics, a spiral approach, was more than a textbook. It was a pedagogical manifesto. It championed a more holistic, student-centered approach to physics education, one that emphasized conceptual understanding, critical thinking, and a lifelong love of learning. It challenged the traditional lecture-based model of instruction, advocating for more interactive, hands-on activities that engage students in the process of scientific discovery. It provided a framework for educators to create dynamic, engaging learning experiences that catered to the diverse needs and learning styles of their students. Parallel with his dedication to education, Baez maintained a strong commitment to humanitarian work. He understood that scientific knowledge was a powerful tool that could be used to address some of the world's most pressing challenges, from poverty and disease to environmental degradation. This conviction led him to become deeply involved in international development efforts, seeking to empower communities with the knowledge and skills they needed to improve their lives. A significant chapter in this work was his presidency of Vivamos Mejor USA, the U.S. affiliate of the Latin American organization Fundación Vivamos Mejor. This organization, founded by his sister Albertina, focused on implementing science-based solutions to improve living conditions in impoverished communities. Baez brought his scientific expertise and his passion for education to bear on this work, helping to design and implement programs that addressed a wide range of issues, including access to clean water, sanitation, healthcare, and sustainable agriculture. Vivamos Mejor's approach was rooted in the belief that sustainable development requires empowering communities to take ownership of their own solutions. The organization worked closely with local leaders and community members to identify their most pressing needs and to develop culturally appropriate solutions that were tailored to their specific circumstances. Projects were designed to be participatory, involving community members in all stages of the process, from planning and implementation to monitoring and evaluation. Baez's leadership of Vivamos Mejor/USA was characterized by his unwavering commitment to scientific rigor and his deep respect for the dignity and agency of the people he served. He insisted that all projects be based on sound scientific principles and that they be carefully evaluated to ensure their effectiveness. He also recognized that scientific knowledge alone was insufficient to address complex social and economic problems. He emphasized the importance of cultural sensitivity,
community participation, and a holistic approach that considered the interconnectedness of environmental, social, and economic factors. His work with Vivamos Megor demonstrated that a scientist's skills and knowledge can be invaluable in addressing humanitarian challenges. He showed that scientific thinking, with its emphasis on evidence-based decision-making, critical analysis, and problem-solving, can be applied to a wide range of issues, from public health and sanitation to agriculture and environmental conservation. He served as an inspiration to other scientists and engineers, encouraging them to use their expertise to make a positive impact on the world. Albert Baez's life resists simple categorization. It is tempting to view his career as bifurcated, a physicist who later transitioned into education and humanitarian work. Such a division, however, obscures the underlying unity of his life's purpose. Baez was, at his core, a problem solver. He applied his formidable intellect to challenges both theoretical and practical, consistently seeking innovative solutions. His initial foray into physics, culminating in the development of X-ray microscopy, was a triumph of applied science. He tackled a concrete problem, the limitations of existing imaging techniques, and devised a novel solution that pushed the boundaries of what was possible. This same analytical rigor, this same commitment to first principles, informed his subsequent work in education and international development. Baez recognized that scientific illiteracy was a pervasive problem, hindering progress and perpetuating inequality. He saw it as a challenge analogous to the focusing of X-rays, a problem requiring innovative solutions, a systematic approach, and a deep understanding of the underlying principles. He approached the challenge of science education with the same creativity and determination that he had brought to his earlier research, seeking to empower both teachers and students with the tools and the mindset needed to explore the wonders of the physical world. His humanitarian work with Vivamos Megor was a natural extension of this problem-solving ethos. He understood that poverty, disease, and environmental degradation were complex challenges that required science-based solutions. He applied his scientific expertise to these issues, working collaboratively with local communities to develop sustainable solutions that improved their lives. Therefore, Albert Baez's legacy is not merely that of a physicist who made a significant contribution to X-ray microscopy, nor is it solely that of an educator who revolutionized science teaching. His legacy is far richer, far more profound. He demonstrated that a scientist's greatest contribution can be twofold: in the discoveries they make, and in their dedication to ensuring that the power of scientific thinking is shared with all of humanity. He proved that teaching is not a lesser calling than research. It is a different application of the same brilliant mind. It is the expansion of knowledge beyond the confines of the laboratory and its dissemination to a world in desperate need of understanding. He showed that the scientific method is not simply a tool for unlocking the secrets of the universe, but a framework for addressing some of the world's most pressing challenges, empowering individuals and communities to build a more just and sustainable future.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.